Hello, my name is Sarhat. I'm a fourth-year PhD student at Stanford University, working with Nick McKeown and Sachin Kati. Today, I'm going to talk about our programmable NIC architecture that allows us to implement transport protocols on hardware. Our design achieves orders of magnitude lower and deterministic latency compared to software-driven approaches while allowing implementing the transport protocols using the P4 language. This is a joint work with Stephen Ibanez, Alex Mallory, Chang-Hong Kim, and Nick McKeown. A typical data center is full of remote procedure calls, RPCs. Essentially, an RPC is a pair of request and response between two servers in the data center. However, reality is not as simple as that. A request triggers many other requests, which triggers many more, and so on. This means an RPC may end up triggering thousands of new ones, and it completes only after the triggered ones complete. Let's make a simple calculation at this point. Suppose it constantly takes 1 microsecond for a client to receive response to its request if no new requests are triggered. Then it would take 100 microseconds for a series of cascaded RPCs with that 100. Again, life is not easy as this. Now suppose it takes 1 microsecond with 99% chance, but 1000 microseconds 1% of the time, maybe because the server is busy with something else. This rare but high latency is the tail for the RPC. Naturally, in such a scenario, multiple triggered RPCs would take 1000 microseconds, and the total completion time would be in the order of milliseconds. In fact, although it would be very rare, an RPC with depth of 100 could take as high as 100 milliseconds. Now, remember that in a typical data center, there are thousands of such RPCs running every second. We are definitely going to hit this high latency multiple times and wait for a long time before the query completes. In short, as said by Jeff Dean, even rare performance hiccups affect a significant fraction of all requests in large-scale distributed systems. Then there's clearly no room for high tail in terms of latency in our future data centers. So if we wish to minimize overall RPC response time, we need to minimize latency in two main locations. The first one is the end host. The RPC processing time at the end host depends on things like complexity of computations, allocated compute resources, memory interactions, and maybe more importantly, thread scheduling overheads such as head-of-line blocking, which overall results in non-deterministic completion time. The second location to minimize RPC response time is the network, where the link capacities, buffer sizes, dynamics of the workload, and the underlying congestion control algorithm determine how quickly a message can be sent from one location to the other. There is one layer of communication that interacts with both of these locations, which is the transport layer. It usually runs as a dedicated thread at the end host while managing the congestion in the network. Therefore, it's possible to get two by one shot if the overall performance of transport layer is optimized. Over the years, a lot of work has gone into accelerating transport and congestion control in software. Let's take a quick look at the state of the art. Google's microkernel approach to host networking, SNAP from CGLOPS 19, reports a tail latency of more than 100 microseconds. Professor John Osterhout's Homa implementation for Linux can deliver an incoming message from the NIC to a user thread in less than 5 microseconds. eRPC optimizes the common cases and reports 850 nanoseconds of wire-to-wire latency for small 32-byte RPCs with timely congestion control. NanoTransport, on the other hand, offloads the transport layer in hardware because hardware can achieve the fastest processing time in a deterministic way. In fact, NanoTransport takes only 6 nanoseconds to run NDP algorithm, allowing a wire-to-wire latency of 69 nanoseconds when attached to the NanoPU client. That's great, but so far I have only mentioned accelerating the transport processing at the end host. If we want to accelerate RPCs, we clearly need to minimize the latency experienced in the network as well. Having an excellent congestion control algorithm is crucial for this, but what if timely or NDP are not the optimal answer? There is growing interest among cloud operators to develop their own congestion control algorithms, such as Homa, Swift, and HPCC. We can expect many more in the future. This diversity of algorithms is mainly due to the different features offered by the already existing networking equipment or the different performance metrics mandated by different workloads. To let operators have this flexibility, we want to let them program the hardware. So in this work, we set out to ask, how much faster would transport layer be when put in hardware while maintaining programmability? This is actually a pretty hot topic. Nandita Dukupati and Konstantin Waits from Google have given a P4 talk last May to stimulate some thought on how to incorporate P4 on NICs for congestion control and transport. The talk had a bunch of to-dos left for a complete design. So today, I hope to give our answer to some of these to-dos by presenting our work, nanoTransport. nanoTransport is a complete programmable architecture, prototyped in FPGA, but designed to go in an ASIC. When programmed to run NDP, it completes in 6 nanoseconds for the small packets, 3 orders of magnitude faster than the fastest NDP reported. He also programmed it to run Homa and Homa plus NDP variant, which we call Homa TR. We believe these, when combined with our HPCC implementation on our behavioral model, will show us that we can implement a relatively large set of congestion control algorithms, and experiments show that they will also run in less than 10 nanoseconds. Our hardware prototype achieves 200 gigabps even with small packets and 11 nanoseconds per packet transport latency, including both directions, while allowing different classes of protocols to be implemented. Plus, it needs to maintain less than 100 bytes of SRAM state per message. Okay, let's take a step back for a moment. These numbers seem incredibly successful, but they are specifically for message-based transport layers, optimized for RPCs. Let me explain why we're doing this. I should make clear that we are interested in applications which will benefit from super low latency RPCs, less than a microsecond. A client sends a short request, the server quickly returns a response. Traditional reliable byte stream protocols based on TCP are not ideal here. First, they require a whole RTT to set up a connection, which takes multiple microseconds. And second, they deliver data as a stream of bytes, which the application needs to parse and delineate. It is much easier if you deliver messages which the thread can immediately use. And third, as all the RPCs between the same pair of sender and receiver are injected into the same byte stream, short RPCs sometimes get queued behind long ones. This is also called the head-of-line blocking. We therefore restrict our interest to reliable one-way messaging service with minimal latency, where the external interface to Ethernet is packets and the internal interface towards the cores is messages. In order to provide this messaging service, we need a couple of blocks to support specific functionalities. First, we need to turn outgoing messages into MTU-sized packets. Packets are stored for retransmission until successfully delivered to the receiver. We call this block the packetization module. 2, turn incoming packets back into the messages. Packets arriving out of order need to be reordered at this stage. This will be our reassembly module. 3, keep timers to cancel messages or retransmit packets. 4, keep state for each message that we can edit in real time. So at 200 gigabps, a 1500 bytes packet is 16 nanoseconds long. This state lets congestion control or scheduling algorithms to decide which packet to send and when. And finally, 5, generate packets for signaling ACKs, NACKs, grants, etc. So here is the key observation. From the list, only the last 2 functionalities require programmability to support different congestion control algorithms. All the others are fixed and relatively easy to implement in hardware. While a similar observation was made in Tonic paper in NSTI 20. Bitmaps keep track of message state and determine which packets to send or retransmit. We keep these bitmaps in reassembly and packetization modules where the actual packets of messages are stored. The difference between protocols is how to modify those bitmaps upon arrival of packets or expiration of time. For protocol-specific modification of bitmaps, we use P4 programmable pipelines that process incoming or outgoing packets and trigger predefined events to tell packetization and reassembly blocks how to modify those bitmaps. So when a data packet arrives, ingress pipeline directly calls the getRx messaging port extern, which fetches necessary state information common to all protocols from the reassembly module for the incoming message. The fetched metadata includes the unique ID allocated to the message by the local architecture, the first unreceived packet or the acknowledgement number in the traditional language, whether the incoming packet was already received before, and whether this message state existed before. This metadata is used in the ingress pipeline to run the congestion control logic of the deployed protocol. The ingress pipeline then may choose to trigger a control packet event that tells the packet generator to create a control packet with specific header fields. A control packet may be an acknowledgement, grant, or NACK, depending on the protocol deployed. And it is sent out to the network via the arbiter and the egress pipeline. The original data packet itself is then given to the reassembly module, which stores it and marks the packet as received within the bitmaps. The reassembly buffer updates the timer for the incoming message so that if the timer expires, all the state for the message is discarded to open up space for new messages. When all the packets of a message are received, they are reassembled in the correct order and they're forwarded towards the CPU cores or the RDMA engine. Now let's look at what happens in the opposite direction. When a message is sent out from an application thread, it is stored in the packetization module, which divides the message into MTU-sized segments and initializes some state variables. Similar to reassembly module, a timer is set in this direction as well. When the timer expires for a message, corresponding packets are retransmitted. As data packets are sent to the destination, control packets arrive to the ingress pipeline for this outbound message, such as an acknowledgement packet. Then, some set of predefined events are triggered from the ingress pipeline to update the message state in the packetization buffer. Here are these predefined events that are triggered by incoming control packets and help modify the state of outgoing messages. The first one is called the delivered event, which informs the packetization module that the packet is delivered to the remote host. This is actually a very simple logic. The sender sets the corresponding bit on the delivered bitmap so that the packet is not retransmitted in the future. Typically, a receipt acknowledgement packet triggers this event. Second, credit TX events signals that a message is allowed to send or retransmit more packets. And it turns out this is also a relatively simple logic to implement in hardware. The packetization buffer sets the corresponding bits on the transmission bitmap, so the permitted packet is transmitted next time the architecture is ready to transmit one. For example, a grant packet triggers this event in Homa. Timeout event is the last event that manipulates a message state. Before diving into how it works, let me describe how timers are managed in our architecture. Both of the ingress and egress timer modules work similarly, except the ingress timer module doesn't trigger retransmissions, but directly flushes the message state from the reassembly buffer. Therefore, I will mainly focus on the egress timer module. For the sake of simplicity and minimal memory usage, we keep a single timer per message. And in order to be able to correctly determine all the retransmissions of a message, we attach metadata to each timer, which keeps track of the highest packets offsets transmitted over the message as of the time the timer is scheduled. Then, when a timer expires, it triggers the packetization module to compute packets for retransmission based on the delivered bitmap of the message and the metadata attached. This ensures that all the undelivered packets that were transmitted by the time timer was set are retransmitted. Finally, a new timer is scheduled for the same message to account for future retransmissions. We verify our programmability capabilities by reproducing figures of various protocols on our prototypes. Specifically, we run challenging in-class workloads in which 10 hosts all send a message to a single server at the same time. Each sender has a message of different sizes, ranging from 20 to 38 packet long. We run two experiments, where one in which the bottleneck buffer size is large enough to absorb the incast, and the other in the bottleneck buffer size is too small to absorb the incast, resulting in packet loss and or trimming. The experiment is conducted using 11 NanoTransport instances running on 11 AWS FPGAs, all connected to a single simulated switch with 200 gigabps links and an RTT of half a microsecond. A high-performance congestion control policy would ensure that the drop packets are retransmitted in a timely fashion while avoiding additional packet drops. For that, NDP uses the concept of packet trimming at the switches, in which data packets that do not fit in the bottleneck queue are trimmed and the headers are forwarded to the receiver with high priority. Those trimmed packets are quickly nacked and the retransmissions are pulled by the receiver. As I mentioned earlier, we have also implemented Homa on NanoTransport and compared it with NDP to showcase how different protocols behave better in different scenarios. Homa is also a receiver-driven protocol, but unlike NDP, it is designed with the assumption that packet loss is extremely rare in modern networks. Thus, it simply relies on timeouts to detect dropped packets rather than utilizing packet trimming within the network. Additionally, rather than using a round-robin pull mechanism, Homa aims to minimize message completion time by approximating SRPT scheduling at the receiver. The figure on the right here shows the message completion time slowdown for each message in the large buffer scenario. We define slowdown as the ratio of actual message completion time to the ideal completion time without any congestion in the network. So smaller is better here. When the buffer is large, no packet loss occurs, enabling both NDP and Homa to smoothly pull grant new data packets from the sender. However, Homa is able to achieve lower slowdowns because messages are granted in SRPT order. So when the buffer size is reduced by half, buffer cannot absorb the entire incast. In this case, NDP is able to achieve lower slowdowns because it enables senders to quickly retransmit lost data using packet trimming and max. Homa, on the other hand, relies on timeouts to detect packet loss. Therefore, it takes longer for Homa to complete the message. So at this point, we leverage the programmability of NanoTransport and implement a new protocol called HOMA-TR, which combines features of Homa and NDP. HOMA-TR incorporates NDP's packet trimming and necking mechanism into Homa so that messages are still granted in SRPT order while enabling quick recovery from packet loss. In the large buffer scenario, HOMA-TR performs exactly the same as Homa because there is no packet loss. However, when the buffer size is reduced by half, HOMA-TR is able to quickly recover from losses and achieve 2 times better slowdowns compared to Homa and 1.5 times better slowdowns compared to NDP. These results suggest that programmability is vital to account for evolving networks, and we can achieve it by writing simple P4 programs onto the NanoTransport architecture. Given that we have a programmable architecture, the next question is how quick NanoTransport is when it comes to process a packet for different protocols. In order to answer this question, we built our prototype using the Firesim cycle accurate simulator, along with the Xilinx SDN, which compiles the P4 code onto the FPGA. The table here shows the RX and TX latency breakdown for our NDP and Homa implementations. Homa is a more complicated protocol because of its SRPT scheduling decisions, so its ingress and egress pipelines have a slightly higher latency. Nevertheless, the transport processing requires at most 7.2 nanoseconds in the ingress path and 3.8 nanoseconds in the egress path, resulting in a maximum transport layer round-trip time of 11 nanoseconds. Naturally, the next question becomes, what is the cost of implementing NanoTransport on hardware? For this, we look at the FPGA resource utilization of our NDP and Homa implementations. To understand the cost of putting the transport layer in hardware, we compare the resource utilization of NanoTransport against a baseline NIC called IceNIC, which does not implement any transport processing. The graph here shows that the logic and flip-flop utilization grows by about 30% for NDP and 60% for Homa. This is as much a reflection of simplicity of the IceNIC as the additional complexity of NanoTransport. And compared to the available resources, NanoTransport consumes less than 2% of the logic and flip-flops of a Virtex UltraScale Plus FPGA. It would require a much smaller fraction of an ASIC. NanoTransport also requires memory for packetization and reassembly, which IceNIC does not need. The amount of memory depends on the number of concurrent messages. So if we design NanoTransport to support up to 16 concurrent 39 kilobyte messages, it needs about 1.2 megabyte of on-chip SRAM. If instead the design supports 128 concurrent messages, it consumes 8.4 megabytes of SRAM, which occupies less than 2 millimeters square on a modern 7 nanometer ASIC. The memory requirement increases linearly with the number of concurrent messages supported. Modern NIC ASICs already include tens of megabytes on onboard SRAM, so that adding the logic for memory is relatively a small additional cost. All right, let me summarize what we have learned from NanoTransport. Our low latency convinces us that delegating the transport layer to hardware without losing flexibility is possible and achieves deterministic tails. We have built complete NanoTransport prototypes with NDP and Homa protocols, which run in less than 11 nanoseconds with 200 gigabps line rate. Moreover, implementing a new protocol takes only a couple of hundred lines of code in P4. And finally, only a few tens of megabytes are required as SRAM for NanoTransport, which is already available in some modern smart NICs. For more details, you can refer to our paper. Thank you.